Hey, what's up? I'm Dave Boyer, aka Mr. Boyer, aka the Swamp Man. I'm here in my classroom in Kernersville Middle School, possibly for the last time for a while. I'm planning on, after Friday, this is Friday, after today, I'm planning on trying to work from home, trying to still deliver these online learning lessons. But I'm going to try to make the most of this last day here in my classroom while I've got the resources that I have in here available to me. So we'll go over the lesson objectives for this lesson. This lesson is about mountain formation. So our first step is going to be to understand what kind of actions involved in the forming of these mountains, what kind of movements are involved. Then we're going to move on to kind of like the step-by-step process of each type of mountain forming. And then we'll try to finish off with my favorite part, probably the examples of mountains that we could go visit, that we could climb, we could explore, we could enjoy in different places around the world. So all these changes to our surface, like a new mountain being formed, obviously these take time, geologic time, long periods of time. But in general, all mountains are going to be formed along plate boundaries. We do have a few exceptions to that with hot spots that we'll have a lesson on a little bit later, but plate boundaries are where mountains form. In the convergent plate boundary activity or lesson that I gave a couple of days ago, we were talking about the Nazca plate off the coast of South America and the South American plate. And the Nazca plate being oceanic and being more dense is subducting underneath the South American plate, causing magma to rise up through the crust there and form volcanic mountains. It's one of the 5 types of mountains that we're going to talk about today. So this whole west side of South America is where the Andes Mountains are. This long chain of mountains forming pretty much right on or right next to this plate boundary. We also talked in that same lesson about the Indian plate slamming together with the Eurasian plate and pushing up the land to form the Himalayan mountains. So plate boundaries are where mountains are going to form in general. But some of the mountains that are here on our planet formed before the current plate boundaries are there. We are here in North Carolina currently, and we have our Appalachian Mountains that run along the eastern seaboard of the United States. Well, that's pretty far away from all the plate boundaries around the North American plate. So these mountains are actually older than the plate boundaries are, or at least where they are right now. If we can keep consistent with the names of things, like keep calling this the North American plate, even if we're talking about 500 million years ago or so, and the Eurasian plate over here, they collided together to form Pangaea, the previous supercontinent. And now since then they have broken up and have spread apart to have the Atlantic Ocean between them at this divergent plate boundary. But when they crashed together and formed those Appalachian Mountains between 1 billion and 500 million years ago, they're now no longer along that plate boundary, but they did form at a plate boundary. So we're going to be taking notes on the 5 types of mountains. Kind of going to go against how I've kind of taught all year long in terms of setting up our pages in our notebook. I still want you to use your science notebook, but I'm going to allow for more freedom for how you set up your pages, how much room you use. You can make those decisions on your own, but we are going to go through 5 of these types of mountains. We'll talk about the action, the process, and examples, and I'll probably stop each video after we're talking about some examples and then show you some pictures of those and then intersperse them in to my eventually the video I'll be putting out on YouTube. So our first type of mountain that we're going to go through is folded mountains. I already kind of talked about those in a previous lesson on convergent plate boundaries, and as I was reviewing at the beginning of this lesson as well. First of all, the action. The action in a folded mountain formation is we have to have convergent plate boundaries, and even more specific than that, our plate boundaries should be continental plate boundaries, continental crust holding up continents. Because if they're both continental plates, they are both going to have relatively equal density, and when they slam into each other, they're going to keep pushing against each other equally, and they're going to push each other higher and higher and higher as it folds. We're going to see that in the process. So we got convergent continental plates collide together. That's pretty good alliteration for our notes here, actually, for language arts kind of concepts too, the CCC language that's in it. Convergent, colliding, continental plates. All right, so let me look at a quick picture of the process. So as we look at this picture, which actually looks a little bit blurry to me, I'm sure it's not showing up too good on the video, but we got a plate coming in here from the left, another plate coming in from the right. So there's our convergent boundary, two plates coming towards each other. They're both continental plates. I'm not seeing that they've drawn in oceans that are above them. So this fits the action, that we just kind of wrote about. As they smash into each other, we can see that the land that's trapped between them keeps getting pushed higher and higher and higher. And as it shows here, often it's not a perfect pushing together. One continent might be moving faster than the other continental plate, and that might allow it to kind of overpower it. But we do tend to get a little bit of some subduction, some one plate kind of being pushed down into the mantle, or just this crack between the two plates allowing magma to come up and add some more rock to the crust that's above it. Well, and as that's added to it and the plates are continuing to squeeze it together, it keeps pushing these mountains up, for the rocks that form these mountains up higher and higher and higher. So that's our basic process of a folded mountain. Going back to hopefully being able to draw that. Think I know how to use this Promethean board by now, but sometimes I'm not perfect. All right, so in this process, we're going to begin with drawing a couple of plates, some crust. We've got a boundary between them, and we're going to call that a continental convergent plate boundary. So, initially this land could be, relatively flat land, but on that leading edge of each of those plates where they crash together, it's going to begin to push on the other plate. So I've tried to draw that, those plates being kind of squeezed together, buckling, meaning that the rock is bending and breaking. A lot of this is going to involve earthquakes. Earthquakes are going to be any sudden shifting of these rocks. So earthquakes are very common in the process of all mountain formations, but for sure in these folded mountains here. And then some key features that we'll see on the surface that can help you identify folded mountains, because our next step is going to be to look at some examples of them. Folded mountains tend to be found in mountain ranges, so in large areas where there's many mountains together, like there are in the Appalachian Mountains and the Himalayas. So we're going to have these kind of rows and rows and rows of mountains, peak after peak after peak. We also tend to have this typical shape of a mountain. If I were to ask a kindergartner to draw a mountain, they'd probably draw this kind of triangle. So you have these gradual slopes heading up to one side and an equal slope heading down on the other side, and they might be connected together in this way. Those are our typical folded mountains. Some examples that I'll show you some pictures from could be the Appalachian Mountains or the Himalayas. Often the best way to see some of these mountains, and I'll try to get some pictures of this in the video, would be to have like rock slides that open up and expose what the insides of these mountains are, because these mountain slopes are obviously going to be covered with possibly trees and plant life, but also possibly snow. But if we have a rock slide, or maybe we've used explosive to open up the mountain to mine for different things, it can often give us a look at inside the mountain and be able to see some of those folds that we're kind of talking about with the folded mountain. So I'm going to stop here and try to add some pictures in, and I'll continue the video with the next type. So we've finished up with folded mountains. If you had Play-Doh at home, modeling clay, and you wanted to make some examples of them, I've kind of done that over the past couple of years. I've kept these for the past 2 years, so they've got some dust and things all around them. But again, our classic shape of folded mountains. We've got our gentle slopes on both sides, our triangle kind of peak to them. Next mountain we're going to move on to are volcanic mountains. I've already kind of talked about those in some of the lessons as well. So you probably are pretty familiar with a volcanic mountain. It's got some key features like the cinder cone top, possibly lava coming out, but many of the volcanic mountains around the planet are actually dormant or extinct. So they don't necessarily all have to have lava at the time that we're seeing them for them to be considered volcanic mountains. But we're going to go through the same kind of process, so you're completing your notes for each type of mountain. Next one, as I said, is volcanic, and we're going to set up over on the left-hand side of our paper the action that's involved, and we'll look at the process and identify examples again of each type of mountain. So volcanic mountains are going to form in very similar ways, at least as part of the action, as to what the folded mountains were. We're going to have convergent plate boundaries. There are examples, I hinted at it before, of hot spots, like Hawaii is not on a plate boundary, and yet Hawaii has volcanic mountains. So we're going to do a separate lesson on how hot spots can create volcanic mountains. But for the purpose of this, we're going to stick to this idea that there is convergent plates, but they are of two different types. So we have continental plate crashing into an oceanic plate. Oceanic plates are more dense than continental plates, so oceanic plates are going to sink. They're going to be pushed downward underneath the continental plate, and that's going to lead to subduction, the process of one plate going underneath another plate. So we're going to try to draw a little bit of this as part of the process. So we're going to have our continental plate over here, and it's traveling in one direction, and it's going to meet up with an oceanic plate, and it is convergent plate boundary, so the oceanic plate should be moving towards them, and they're going to crash together, collide together. The continental plate is less dense. Less dense is going to be able to remain on top. More dense means it's going to sink down below. Drawn this as blue because it's oceanic, but I fear that that's going to be very misleading. This isn't that the oceans are pushed underneath the continental plate, it's that the rock that the oceans are sitting on top of, often limestone and basalt rock, some of this can be really thick layers of rock that the oceans are sitting on top of. So I've drawn it in blue for oceanic crust, not because it's the ocean. If we were to draw the oceans would be up above this still. But anyways, we've got subduction, so we got the oceanic plate being pushed underneath the continental plate. Underneath that continental plate is underneath the crust is the mantle, an area of heated rock, liquid rock, and as the crust is pushed down into the mantle, this leading edge is going to begin to melt into liquid rock also. Well, the mantle's already full with rock, so it can't really just keep adding more and more and more rock on this edge of subduction. So as this rock is added down here, it's going to increase the pressure, the density in this area. And fluids can't really survive they can't be stable when there's differences in pressure. So if we have higher pressure here than anywhere else, it's going to start to spill over and fill in some of the lower pressure areas around it, but it's going to try to find its way to the least amount of pressure, and that's up above the crust. So it's going to push plumes of magma up and start melting the bottom of this crust that's there. And eventually it's going to push high enough to spew out the top of the land, the top of the continental crust. And then as that magma begins to harden and form into rock, we can get our volcanic mountain. So classic shape of a volcanic mountain, kind of did that for the folded mountain just before. But the classic shape of a volcanic mountain is that we've got our sides, and at the top, especially after it has recently erupted, is going to have that cinder cone shape to it, where the lava has blown off the top, mostly with the gases actually, not with the lava. This crust that's here, this rock, especially the limestone there, can be embedded with tons and tons and tons of fossilized organic material that was on the oceans that sank down to the bottom of the oceans and then became a part of this crust. So as that carbon is pushed down into the mantle, it's going to form carbon dioxide gases and some other gases, and gases are going to really work to try to find their way to lower pressure areas. So the gases are often the aggressive material that is pushing through and kind of forcing open the crust and then spewing out. And so often the cinder cone is blown off by the gases coming out, more so even than the lava. So that's a volcanic mountain. We'll take a look at some examples of it and then move on to our third type. All right, so the third type of mountain that we're going to talk about are fault block mountains. So you might be able to see my modeling clay example here. And then if we took a look at this cardboard box model up above it, we've got a good look at kind of the classic shape of a fault block mountain. So let's go ahead and talk about the actions that are involved in the formation of fault block mountains and the step-by-step processes, and then we'll see some examples of fault block mountains from around the earth. So, going back to your notes for fault block, fault, F-A-U-L-T, like it's not my fault, is what I keep hearing from students all the time when they're accused of something. But a fault in geology and science is a crack in Earth's crust. So the action involved is definitely driven by earthquakes. So earthquakes are going to crack the crust, open up new faults, and then once we've got cracks in the crust, then these chunks of rock, these blocks of rock, are free to move independently with the forces that are coming from convergent and divergent and transform boundaries. So that allows a piece of rock to lift up. That's the main action that we're seeing here. So if we go to looking at the process, move this up a little bit. So I'm kind of going to start basically the same way I've done others. We're going to have our crust that's here, but then we have earthquakes that crack the crust, that form fault lines. So once we have our fault lines, each of these chunks of rock that I've drawn in right here could be pushed up higher, could drop down lower, could be pushed inwards or separate apart from each other. Whatever the forces are doing, once we have chunks of rock that are free to move, we have the potential for the formation of fault block mountains. So if we look at this image here, we had our three kind of sections of rock that I had just drawn in there, and it looks to me like this piece over here on the left has been pushed upwards. And as that pushes upwards, other chunks of rock that are touching it can be moved, from those forces also. So this middle piece kind of slides down a little bit, and then we've got our kind of stationary block over here on the right side. So we've got three terms for places in a fault block mountain. These are not terms that you have to know. You don't need to write them down. But this piece that was lifted up is called the horst, and then it often has a near vertical ledge that drops down called the scarp, and then the next piece that had slid down is called the graben. So I'm going to set my camera down and kind of go through that with my cardboard box model with you real quick, and then we'll take a look at examples. So we've got our 2 pieces of chunks of rock right here, and maybe we've got an earthquake and a crack in Earth's crust. Once we have a crack in Earth's crust, maybe the forces are going to lift up a piece of rock. Once we have rock lifted up, we can call that a mountain. So this piece here, the flat land, or it's not always flat, but it is in this box model. The piece that was lifted up is called the horst. Then we've got the scarp and the graben. One thing that we can really see with this cardboard box model that I like is that the blocks that they've drawn in with this blue color in here we're able to track kind of where those rocks move during these earthquakes or during these mountain formations. So possibly we have stuff that gets lifted up like this, and then maybe some other forces cause, especially if we have this ledge kind of hanging over a lot and gravity's going to pull the top of it down because we got a lot of potential energy there. Sometimes we can get rock that will fall down, and now we have rock, the layers of rock aren't lined up with each other anymore. We've been able to see that in examples around. I've got a YouTube video actually from Linville Falls area talking about the same exact concept. So anywhere we have earthquakes could be locations where we could see fault block mountains, whether they're earthquakes now or have happened long ago. But some places that I've been where fault block mountains are found, I just mentioned around Linville Falls area, we can have some of that, although the general Appalachians tend to be more folded mountains. But even within folded mountains, each individual mountain could have a different cause, could be a different type of mountain, as we're going to see in some of the next examples as well. But the West Coast, the Sierra Nevada mountains of California particularly, are really good examples of fault block mountains. We can also see fault block mountains in some other national parks that I'd love to get to. Hopefully going to get to this summer if things will actually calm down here. But in Grand Tetons National Park in Wyoming is a great examples of fault block mountains. I'll try to show you some pictures of those. So fault block mountains, again, the key idea is that we have earthquakes, and earthquakes crack the crust and then allow chunks of rock to be lifted up to form those fault block mountains. All right, so the 4th type of mountain that we're going to talk about are Plateau Mountains. Plateaus are something that you should study as one of the geographical features in social studies, but also one of the types of mountains that we're learning about here in science. So you're probably pretty familiar with kind of the shape of a plateau. Probably aren't very familiar with how those plateaus are created, plateau mountains. So here's our notes on that. Plateau is one of our 5 types of mountains. We've got our action listed over here on the left, and kind of a long description of the action here. There's a lot of stuff going on to lead to having those, tall columns with the flat tops on them that we typically think of as plateaus. So it begins actually below the surface. We have columns of magma. So that's liquid rock coming up from the mantle into the crust and rising up in these streams coming up. And they cool down and harden under the surface to form hard rock, solid rock. But then the rock that's around them that was there as part of the crust before is going to get weathered and eroded and moved out of the way to expose those plateaus that were actually buried under the rest of the crust. Kind of complicated stuff. Hopefully a couple of drawings in the process will help us understand that a little bit better. So we're going to add to this the process. And we'll look at examples of Plateau Mountains a little bit later, but my favorite example I've been there twice. Actually, went once when I was in 6th grade. I went with my grandparents to a place called Devil's Tower in Wyoming. Really cool mountain. And then I went back, actually probably almost a decade ago now, but when my now wife and I were just dating, we did a road trip through some of the Midwest and Mountain West, and got to see Devil's Tower then, and just a really, really cool place to see. But we're gonna go through the process there. So Wyoming, where Devil's Tower is pretty far away from plate boundaries. It's kind of like the center of the North American plate. So this doesn't necessarily isn't necessarily all about plate boundaries. So we're going to start with some land, a block of land, relatively flat, like some areas of Wyoming are. And underneath that, we have some action happening. So we get some magma that starts to rise up. Well, we've studied why it would rise. We've got maybe a hot spot, a hotter area of the core underneath here that's causing that magma to rise pretty quickly as part of these convection currents. But as that magma starts to touch the bottom of the crust, it begins to melt the rock that's there and push it out of the way. So these columns can rise up into the crust. If they were to spew through the crust, break through the crust, they're going to form a volcanic mountain. But if, as they get away from this heated area of the core, if they rise up through the crust and they get cooled down by the rock, they're exchanging their heat energy away from them and into the rock around them. If it's not enough energy to keep going, not enough pressure difference to keep pushing up and cause a volcano, then this magma over time is going to cool down and harden into solid rock. So it's kind of hard to teach this unit sometimes because you never know what to teach first. Things are all kind of connected together. We've definitely done convection currents, and that should help with this. But another key difference or key concept that we haven't talked about yet are different types of rocks, the 3 main types of rocks. You should be exposed to those from elementary school, but we have sedimentary, igneous, and metamorphic. And the 2 that are involved here are going to be igneous rock, because magma cooling down, lava cooling down forms igneous rock, and then sedimentary rock. In general, most flat land is going to include a lot of sedimentary rock. Sediments build up, organic material builds up and gets pressed down over time and squished together to form and cement into rock. So all this that I put in the green area we're going to consider that to be sedimentary rock. And this that I just outlined in the black, and hopefully did some nice columns here to make it look like Devil's Tower when I'm done, that's going to be our igneous rock. So in our second step of this process, we're still going to have our land that's there, but over time, all this sedimentary rock is generally easier to break apart. It's not as hard as igneous rock is. So, we're in the plains of Wyoming, and there's really heavy snows and cold temperatures during the winter. We get desert rains, heavy winds, and cold temperatures through the winter, but also wind blowing across these plains, really strong winds blowing across the plains. And all that forces are going to start to knock off. And you don't have to do this on your notes. I'm just going to kind of show you the process here. But it's going to strip away the top layer of rocks over time and keep stripping it away and blowing it further and further away. And rain's going to cause the dirt and rocks that are around that to keep breaking down, keep moving further and further away. And eventually it's going to expose the top of that plume of magma that was cooling down and hardening inside the crust. So the erosion and weathering, that's breaking down rock and moving it based on forces like wind, water, temperature, moving away that easier to break apart sedimentary rock and leaving behind these columns of igneous rock that are a little bit better able to withstand these forces of weathering and erosion. And so you end up with the Plateau Mountain. I'll show you some pictures of some pretty cool Plateau Mountains. I've got two that are kind of my favorite, and then one that kind of looks a little bit like a Plateau Mountain, and you could go to today if you wanted to. It's not far away. All right, so that brings us to our last type of mountains of the 5 types of mountains, dome mountains. So let's go ahead and get kind of our action and our title set up here with dome mountains, D-O-M-E, dome. You should know the shape of a dome. There's plenty of famous sports places that use domes. There's the Carrier Dome where the Syracuse Orangemen play. Carolina's had some pretty good success there. We got the Houston Astrodome where they play baseball, and then the New Orleans Superdome. So a dome, we should be thinking of this kind of rounded top, rounded roof. So a dome mountain is going to have that same classic shape, a rounded top. So here's our action for that. It's going to involve magma coming up from the mantle, pushing up through the bottom of the crust. But it's not going to break through the crust. If it breaks through the crust, then we've got lava, we've got a volcano, a volcanic mountain. So instead, this lava is going to push up into the bottom of the crust, and that hot liquid rock is going to begin to melt the rock of the crust and start to bend the rock that's above it as it puts pressure on that. So let me kind of try to demonstrate that for you real quick. I'll switch to one of my little models. So here's our flat earth, flat land that's there. Sorry, earth is not flat, but there is flat land on earth. But magma is going to start to push up from the mantle down below it and heat up some of this rock, make it more plastic-like, make it more bendable. And as it does that, it's still applying that pressure from down below. And the land just starts to push upwards and upwards and upwards and upwards. And as long as that top layer of rock can hold the pressure, can hold the magma from escaping and turning into a volcano, it can form a mountain with this rounded top, a dome mountain. So taking a look at an image of that, basically the same idea as what I just described. Magma pushing up into these plumes, these columns of liquid rock rising up through the mantle, through the bottom of the crust and collecting on the bottom of the crust. As that increases the pressure there and increases the temperature of that rock and melt some of that rock or make it more movable, it can create this bulge, this rounded top to it. And that's our dome mountain shape. So we'll try to draw that in just a little bit here. Let me push this up. There we go. And this is the process. So in the process, just like in these others, we're going to have some block of land, some piece of crust that's there, and underneath that we have this rising plume of magma starting to push up onto the bottom of that crust. Slide it up a little bit more. So in our second drawing that we're going to have of it, we'll kind of get the shape going there. And this magma is going to be applying some pressure, pushing and melting the rock around it, giving it that classic dome shape. It's not the most common type of mountain. Often this melting process underneath the earth can continue and allow that magma to seep up and erupt as a volcano. Or sometimes we don't get this rounded, we get that column that we saw with the Plateau Mountains, and then the erosion, weathering and erosion around it. But in this case, the rock of the crust is able to withstand the pressures coming from the magma down below, but it's just warped its shape. bended it into this dome shape. Plenty of great examples around. It's not the most common, like I said, but in our area, we've got one of my favorite examples to go to is Stone Mountain, the Stone Mountain, North Carolina, Stone Mountain State Park in North Carolina. Great couple-mile hike to get up onto the top of the dome. Beautiful views from up there. You can really see some of the changes to the surface that happen there on Stone Mountain. We get a lot of these little pockets. I've done another video from on top of there with my daughter Belle with me, where the water pools up, and if it freezes overnight, that water expands, pushes outwards, and is actually digging little holes, little pockets on the top of the mountain there. Maybe another cool example I've seen from afar but haven't hiked up on top of it yet is Half Dome Mountain in Yosemite National Park, California. So hopefully you'll check out some pictures of that. Heck, I'd recommend you search YouTube and find some video of some guys climbing or girls climbing Half Dome, because it's a pretty gnarly climb. So we got our 5 mountains here. I'm going to go through them real quick just as a quick review, and then we'll call an end to this lesson. So our first type of mountain we talked about, we have folded mountains. That was the convergent continental plates colliding, pushing on each other, that pressure lifting the rock upwards and folding it around. We then talked about volcanic mountains. The example we used was subduction, where an oceanic crust is subducting underneath a continental crust, melting into liquid rock, increasing the pressure there, and then that rock forcing its way up out of the top, blowing a hole through a cinder cone hole out of the top, and cooling and hardening once it's on the surface to form the mountain. The third type we went over was fault block mountains. Fault block, the key term to remember there is earthquakes. And each of these, as you should be able to tell, has a unique shape to it. In the fault block, we've got this gradual slope heading up of the Horst part of it. Then we have the steep slope that goes straight down there, the scarp. Then it gets down to the flat land down below it, the Gabon. Fourth type of mountain we did was Plateau Mountains, some of the most unique types of mountains. You can see them in Monument Valley, Arizona. Hopefully I'll have pictures up during this video, or already had pictures up during the video. Devil's Tower, and even Pilot Mountain in our area. And then we just finished up with the Dome Mountain. Dome Mountain has that classic rounded top to it. You might be able to see in here some of those little pockets I was talking about. So that's the magma that was coming up, not the pockets, but the magma was rising up through the crust, melting and making the crust more pliable. Then it warps the shape of it, rounds the top of it as it lifts it up. So there you have it, 5 types of mountains. One of my favorite things to be on outside. So I think it's pretty neat to learn how they're made, kind of learn more about their histories as you get to explore more and hike on some. You can really kind of tell some of those classic shapes, but just want to stop here and share a little bit about that with you, tell you that science rocks. Peace.